Right. So now we looked at posterior predictive checks. So we checked whether the predicted values based on the model fit or match, approximate the original values that we used to estimate basically the model. But another thing that we might want to do at this stage is to run a so-called sensitivity analysis. And in this case, it's a prior sensitivity analysis, meaning that we check the degree of influence that the priors had on the posterior. Right? That's why it's called a sensitivity analysis. We want to know how sensitive the model was in relation to the priors. I'm not going to go into too much details here, and the code, you can have a look at the code, but basically what I'm going to be doing now is extract the parameters, the estimates of the fixed effects, and then by doing some calculations that I'll show you in a second, we can produce a plot that helps us get a sense. It's not a quantitative assessment of sensitivity, but it's more qualitative based on quantitative values that can basically show you whether there are problems with the prior specification. So with this code, I'm using the tidy function from broom.mixed package, but this code just returns basically the term and the estimate with the standard error and lower and upper confidence interval, right? And once you get that object, you can go through this code, which is going to plot the plot that I was just mentioning. And what I'm doing here is you need to specify two variables here. One is theta, which is the mean of the priors for the fixed parameters here, right? And since we used regularizing priors, they were all centered on 0. So here you can just go with 0. And it's just 4 because, in fact, this data set has only 4 fixed effects, right? Because there were only 4 fixed effect parameters in the model. So if you have 10 fixed effect parameters in the model, this data set, this table will have 10 rows rather than just 4. And what you do basically is for each of those parameters, you have to declare the mean of the center of the distribution. And since most times we use a normal distribution with mean 0, that's going to be 0. And then you specify the standard deviation of the prior corresponding to the mean in theta, and that is sigma prior, right? It's just the sigma, the standard deviation of the prior. And if you remember, we used a normal distribution with mean 0, standard deviation 3 for the intercept. And then we used, for all the parameters of class B, we used mean 0 and standard deviation 1. And now with theta and sigma prior and the estimates that we got from this code, basically, we can calculate two values, two parameters. One is Z, which corresponds to the so-called posterior Z scores, and I'll explain what they are in a second. And the other value is S, which is the posterior shrinkage. And these two values combined together will help us visualizing basically the sensitivity of the model relative to the priors. And S is going to be bound between 0 and 1, and the higher, the better. So the higher value means that there has been greater posterior shrinkage, which means that your posterior is thinner, is less wide than the prior. And you do want that, right? You do want your posterior to be more informative than the prior. Otherwise, there would be no point in doing Bayesian updating, basically. So the higher S, the more shrinkage there's been of the width of the posterior, where 0 means no shrinkage at all, and 1 means the greatest shrinkage possible based on the model and the data. So you want S to be as high as possible. Z, as I was saying, it's the posterior Z scores, and the posterior Z score, you want that to be as low as possible, and it's only positive values. So you have 0 and above, and generally you should think about values between 0 and 5 approximately, and you want Z to be as low as possible for your model. And what the posterior Z scores tell you is how much of the presumed generative process, basically the family distribution that you specified, how much of that has actually made it through from the priors to the data onto the posteriors, right? And you do want that, you do want the posterior Z scores to be as slow as possible, because when it's slow, it means that indeed the expected generative process that created that particular distribution has made it into the posterior, right? And sorry, it sounds very complicated, but now that we're going to see the plot, it's going to be clearer. And never mind about the formulas. These are taken from a paper. I forgot to include the reference here, but we can point that out to you. There's a paper that explains why this is a method of a good method for doing prior sensitivity analysis. This is not the only one. It's a quick and dirty one, but it works pretty nicely. And there are other ones that I'm not going to discuss, but this is a good start. So let's plot this. There you go. I thought sorry, this one first. I spoiled it. Anyway, so you have S, which is the posterior shrinkage on the x-axis, and you want that to be as high as possible. And then you have Z on the y-axis, and you want it to be as low as possible. And for each parameter of the fixed effects, you basically get a point for a specific S value and a specific Z value. Since you want S to be as high as possible, basically 1, and you want Z to be as low as possible, basically 0, you really want, what you want to see with this plot is that everything concentrates on the lower right corner of this plot, right? And in fact, this is what we see here, right? Like more or less these 4 parameters actually concentrate on that in that area. Here, I'm just showing you the sensitivity analysis for the fixed effects, but of course, you can also do it on the group level or random effects. I just did it here with the fixed effects because we have so many parameters that I would have to plot, like a bunch of parameters with several different separate plots, because otherwise we wouldn't be able to see much. But let's go a little bit deeper on this idea that you want these, this dot to be in the lower right corner. And this is what I spoiled before. I hope it's big enough. Perhaps let me do this. There you go. Can you see it? If not, the labels have disappeared. That's a problem with our studio. But what this thing is showing us is that you have basically 4 quadrants, let's say, and the bottom right quadrant says ideal here, because it means that ideally you would want to see those dots in that quadrant, right? And when you get the dots there, it means that your priors were fine. It means that they were like weakly informative, not too much, but not too much, right? That they were just the right amount. On the other hand, if the dots are in this quadrant where it says overfit, it means that the model is overfitting the data, which means that the prior are so weak, are so basically uninformative that it's basically like setting flat priors. And you do not want that. You want to stay in the ideal quadrant, right? You don't want the model to return estimates that are too specific to the sample that you collected. You will see that I was actually surprised that the intercept, it's here, it doesn't say, but this is the intercept. We're really, really good with the intercept, basically. Like it's basically S1 and Z0. Very generally, the intercept will be slightly overfit. And that is because we're using weakly informative and regularizing priors, but it's fine. It's not a problem if you have it, but you have to remember that if you're overfitting the intercept, it means that in fact, the real value might be somewhere, slightly somewhere else. The real issue is when all of the parameters are in the overfit quadrant. Of course, just a word of warning, Z can be higher than 5. I had models that returned me a Z of 25, 50, sometimes even 100. I'm just plotting between 0 and 5 because basically anything above 5 is bad. So if you plot something that is constrained between 0 and 5 and you don't see your parameters, it's probably because they're above 5, right? And that means that perhaps the priors were, if they are on this side, it probably means that the priors were not informative enough. Definitely, for some reasons, it never happened to me before. I never had parameters on the left side, and that is very likely because we use weakly informative priors, right? Because when you have S that is below 0.5, that is towards 0, it means that the priors are dominating the posterior. That's a technical term. You know, if the prior dominates the posterior, it means that the data basically hasn't had any contribution whatsoever to the posterior. So you could have not collected data and used the priors, and the model would have basically gave you the same answer. And the difference between these two quadrants is that if Z is low, the model is poorly identified, which means that you got the family distribution right, but the priors were not basically good. They were not informative at the right degree. If instead you get parameters up here, and this says prior posterior conflict, which means that your priors were, that the priors you specified and the posterior that you got are so far away from each other, are so different that they conflict with each other, which means that your priors were possibly too informative, right? And it also means that not only your priors were too informative or weakly informative in the wrong direction, but also that you got the generating process, the underlying generating process wrong, meaning that perhaps you set a family distribution that is completely off in respect to what the data actually is. So that's basically it. If you follow the code for calculating S and Z, then you can just plot it. And in this case, copy paste really should work. You just need to change the theta variable and the sigma prior variable based on the priors that you have specified. And then you can plot, you can just plot the thing and you can see where the parameters are. So with this, for example, in your paper, you can simply say that you run prior sensitivity analysis using the method by the guy that we'll send you the paper of, and that this sensitivity analysis didn't suggest issues with the prior, and then you can point the reader to the appendix where you show them the code and the plots and everything, right? So I assume most reviewers and readers will not be interested in knowing exactly where these dots are, but they can check if they want that you didn't tell a lie, but of course I'm not expecting anybody to do that. So that's basically it. That's a way of doing a sensitivity, a prior sensitivity analysis. If there are no questions about this, I think we can move on. And I guess it's Timo now, but perhaps there are questions.
Let me check.
Yep.
Yeah, indeed. If you do end up with a very high Z in overfit quadrant, to make priors less weakly informative, would you just reduce the sigmas?
Yes, exactly. That's one way. Of course, if the intercept is very far removed from zero, then in that case, you might, like by reducing sigma, you might actually exclude the intercept. It never really, I mean, I never really had this issue, but I really like talking about milliseconds because I think it's easier to grasp than probabilities, for example. But if your intercept is like 150 milliseconds, with which, you know, like for an English vowel is potentially, you know, on point, if you specify a prior that is centered at 0 with a standard deviation of 50, it means that, no, that's not true, sorry, that no, because you're on the locked space. But let's assume that you set a prior that basically means that at 95% confidence, you want to include values that are between 0 milliseconds and 100 milliseconds, then you're going to get the opposite. You're going to get the prior basically is too strong because you excluded the actual intercept. So at that point, if you have strong reasons, conceptual and practical reasons to not using a regularizing prior, then you can set the mean to something that makes sense. And if you remember, we did something like that for F0 before, like we showed you a distribution that was centered at 200. I recommend going with a regularizing prior, and if the intercept is overfit, you don't really have to worry too much, unless you really care about the intercept. But with weakly informative priors, it's fine if the data basically overcomes the prior. And with the posterior that you get with that intercept, when you run another experiment on a similar thing, you can use that knowledge that you got from the previous study.
On that, there are a couple of questions that kind of tie in with that. So if you do end up with no, sorry, that's the wrong one. But if you do have strong prior beliefs, justifiably, let's say you have a series of experiments and you estimated the parameter and then want to use that for a prior, and the prior dominates the posterior, does that just mean that the data aren't enough to change your mind?
Precisely, yes. Basically, the stronger your prior belief, the more data you need to change your mind, right? And this is very intuitive. This is part of what we were saying, that in reality, frequency statistics is not that intuitive because you're talking about experiments that you have never run and that you run multiple times, and it's very weird. With Bayesian, instead, it's way more intuitive. And if you think about it, like if I say, I really, really love chocolate ice cream, like I really, really love it. For you to convince me that chocolate ice cream is not nice, it's not good, it's not tasty, you really need to bring in a lot of arguments, right? Because, I really believe that chocolate ice cream is the best. That's probably a better way of putting it, right? And if you want to convince me that vanilla ice cream is the best, you really need to bring a lot of evidence, basically. If, on the other hand, I don't give a damn about ice cream and you come to me and you give me one reason for why chocolate ice cream is the best ever, I will basically believe you, right? Because I don't have any prior expectations about what is the best ice cream. And if you tell me it's the best because it's brown, I will say, yeah, why not? Right, this is a stupid example, but like it really tells you how intuitive doing Bayesian statistics is once you get all the concepts basically laid out. So yeah, the stronger the prior, the more basically the greater the sample size is, unless the effects that you're looking are unless the standard deviations are so small, like basically every speaker, every listener does exactly the same thing, then at that point you won't need much data. But we know, and I'm sure like everybody knows, that's never the case. It could happen that it so happens that you're looking at something that is, like it's always exactly like that, like 10 milliseconds, nothing else, then you don't need as much data. But most times you will need more.
One last time on that one, not on ice cream, but on individual differences. What happens if you try to fit a model with not enough data? We just covered that, like trying to estimate individual effects, but you only have one item per cell.
This is a brilliant question, and that's again the beauty and the intuitiveness of Bayesian statistics. When you don't have enough data in frequency statistics, the model craps out. Basically, the model doesn't fit, doesn't converge, or it gives you like estimates that are completely crazy. With fitting a Bayesian model will always give you an answer, but the uncertainty around the answer will be basically correlated with the amount of evidence. So the smallest amount of evidence you have, the greater uncertainty you will get out of the model, which in practical terms means a wider probability distribution, right? So for example, if you're interested in individual differences, and the posterior of the standard deviation of that particular random effect encompasses values that are, from I don't know, from minus 100 to plus 500, whatever the scale is. What can you say about that? You cannot really say anything. The uncertainty is so high that you only know that any value between minus 400 and plus 600 are possible. So you can still do it, but perhaps like this term especially in computational disciplines, garbage in, garbage out. With Bayesian, uncertainty in, uncertainty out, right? So that's why we need big sample size if we want to be more certain about estimates.
Great, I think we covered much ground. Again, priors. We are aware that this is the most confusing part, especially when we show you logistic regression. And this is also the one that will require the most work and thinking. And we're in the same boat. We still learn a lot as we go. So don't be terrified by it immediately. As Stefano said, usually the posterior dominates the prior. So it's important, obviously, to set priors, but the specific parameters, if we stick with something weakly informative, are usually not a deal breaker, right? So I hope that helps a little.